All right. Good morning. Good afternoon, all. My name is Rudy Shankar, Director of the Energy Systems Engineering Program. And we are going to be having the students talk about their final project results in the project symposium. And so there are 3 projects you hear about. There are 4 people. So one project has 2 people working on it. Now, time-wise, I've allocated rationed 30 minutes per person. So the first team is consisted of 2 people. They'll take about an hour to present, which includes time for Q&A too. And then the next person will present for half an hour. The third project will be for another half an hour. So nominally, it'll take about 2 hours to go through the program. Now, in the mail, you should have gotten the booklet that Susan just prepared on the Capstone Projects Symposium.
It was sent out electronically, yes.
You got it electronically, so there's a description of projects and the people and really the class of 2024. And so it's more details there. Just some other housekeeping items before I turn it over to the students. You also should have gotten electronically the evaluation forms. So you'll have a chance at the end of the presentations today to go over your assessment of what you heard, and then just complete the Google form, and that'll give us the information we need. All right, now, any questions before I start?
Yeah, Rudy, it's Al. I did not get either one of those emails from Susan.
Okay.
That's because your email keeps bouncing back, Al. Remember, we had that. I'll send the evaluation form as a link in the chat here so that everybody has it again.
All right.
All right.
All right. Thank you.
Yep.
All right. Any other questions before we start? So normally 2 hours, and then question and answer at the end of each of the talks. And then we will have half an hour or so to finish the evaluation process. All right, so let me introduce the first project team, Mohammed and Ahmed. And so take it over. I've got to do this. Sorry about that.
Yes, just make sure your mic is the speaker is on. The speaker is on.
Yeah. Then you turn your speaker.
Hello, everyone. My name is Ahmed. Can you hear us well?
Can you hear Ahmed and Mohammed?
We can hear you.
Hello?
We can hear you, Ahmed.
Okay.
I hear you as well.
Okay, sounds good. Good morning, everyone. My name is Ahmed. I am ESE master student. My background is mechanical engineering. Graduated in Egypt. I am PMP certified and MPA. An experience with over 15 years in maintenance and the projects field. I have been engineering and maintenance manager from 2020 to 2023, and maintenance manager from 2008 till 2020. Now introduce my colleague Muhammad.
Hello everyone, welcome to our energy system engineering capstone project. My name is Mohammed Morsi. I am a graduate student at energy system engineering. I'm certified energy manager from Association of Energy Engineers from 2021. I have a bachelor degree from Alexandria University in electrical engineering. Graduated in 2013. I worked as a utility and energy team leader at Data Perla Group from 2019 to 2023. I worked with Siemens Energy as combined cycle power plant operation engineer from 2016 to 2019. And I worked also as electrical and instrument engineer in Petrojet company in the oil and gas field.
So we are today introducing the project for Lehigh University Intelligent Power Virtual Power Plant Feasibility Study. Before we delve into our project, we would like to acknowledge the contribution of our sponsor, Dernetsoft, the campus facility leader, Mr. Doug Spingel, and of course, our esteemed Professor Rudy Shankar. The agenda for today's presentation is background about the project and the objective, Lehigh University sustainability goals, and exploring the potential at the campus, project progress up to date, virtual power plants definition. This part will be introduced by myself, starting from technical discussion results and future plans. This will be introduced by my colleague. So for the background, the campus is consuming around 67 gigawatt hour of electricity. This based on last year 2023 bills, with cost around over $6.7 million. The peak load for the campus is 14 to 15 megawatt, producing 72,000 million metric ton carbon dioxide equivalent. The campus has around 180 buildings with around 4.5 million square foot available for rooftop solar panels. The campus as well has 5.2 kilowatt of solar generation, but still not connected to the grid. The project objective is to assess the potential for the campus to provide great service through aggregation of intelligent virtual power plant, support the achievement for the financial, environmental, and operational targets, develop a detailed simulation for the integration of distributed energy resources, and present the finding derived from the exploration of the project. Regarding the sustainability goals of the university has 13 goals for resilience and greenhouse gas emission. Our interest is in two goals. For goal number 11 is to offset 100% of the electricity consumption with renewable energy through a combination of off-site and on-site projects, energy conservation, and renewable energy credits. Goal 12 is to seek additional renewable opportunities to offset natural gas usage as per climate strategy. Going into the potential at the university has a capacity to integrate distributed energy resources presented in rooftop solar and batteries to enhance its resiliency and reliability. This will lead to energy saving and, of course, greenhouse gas emission reduction by using these renewable resources. Ultimately, this will lead to financial impact as participation of demand response program. Project progress. We have last semester, fall 2023, we have studied the existing emergency generators to curtail campus loads. We have done simulation for participation in economic demand response program. We have evaluated different tools of the demand response program, and we selected the best suitable tools for campus contribution, resulted in achieving revenue with 4-month return on investment. In this semester, we have done a background research based on the available assets at campus, as well as review for the demand response program. And then we have done data collection and simulation through the load profiles for the buildings and analysis for the distributed energy resources via programs of REOPT and Helioscope, as well as developing selection model through rating index metrics and the contribution from Dernetsoft neural network model, which lead to the simulation of the demand response program. Based on this, we have made the assessment in terms of operational, financial, and environmental for the results. A virtual power plant, in a brief definition, is an interconnected network of distributed energy resources, such as solar panels and batteries, managed centrally to optimize renewable energy utilization, grid stability, and participation in energy markets. As shown in the graph, the virtual power plant has inputs and outputs. Inputs from different distributed energy, like batteries, solar panels, generators, demand response. The virtual power plant is like a brain to predict, optimize, aggregate the best demand, the best resource energy for selection, for evaluation, and to contribute in the demand response program. Similar to our projects, we have explored as a part of our background research, similar universities like Queen Island Project and University of California. Queen Island University have done batteries project. The project rated power is 1.11 megawatt. The storage capacity of the batteries is 2.15 megawatt. The total project cost was around 2 million and commissioned in 2019. The project revenue for the first quarter was around $80,000. As shown here, the battery earns revenue by charging when energy prices are low and discharging during the prices are high. the prices ranges from $11 up to $34. Battering being charged at low prices and then discharged to the grid when the prices become high around 34, which generates revenue for the campus. Another example on the right-hand side for the University of California. California has implemented 30 megawatt combined heat and power system with 2.8 megawatt fuel cell. Consists of 2.4 megawatt solar panels and 2.5 megawatt energy storage. The payback for the project was around 4 years, and it was commissioned in 2020. For the technical discussion, my colleague will introduce this part.
Thank you, Ahmed, for providing this introduction about our Capstone project. As Ahmed mentioned, we are seeking to make visibility study for a virtual power plant at Lehigh University. In this part, I will start the technical discussion about our project. Our project passes through many steps. The first step of this project is the data collection and ingestion in the DIRNet software platform. As shown here in photos attached, we collected the Lehigh Shark meters, which is around 180 meter for electricity of a building. This is done by cooperation with Lehigh University facility team and Lehigh University Library and Technology Service. The data is automated, extracted from Lehigh server to be added and integrated with DIRNet software platform. The second step in our project, we review the existing building at Lehigh University, which is around 180 building, and we searched to find the potential site for installing the rooftop solar. During this search, we are looking for solar access for each building to ensure that the sunlight exposure without shading for each building, beside reviewing the roof size and shape of each building to ensure that it's applicable for solar panel installations. Blue images showing examples for building detected at Lehigh University. One of them is the central heating building, and the second one is the health center and molar lab, besides the business and innovation building and IMBT laboratory. During the last year, the project is started since 2019 under DIRNet soft supervision and sponsorship. During the last year, energy system engineering student found around 26 buildings, and this year we found additional building that will be potential for installing the rooftop solar, around 5 buildings, and now we have total around 31 buildings available for rooftop solar installation. After selected the 31 building from 180 building at Lehigh University, we conduct a heloscope simulation to find the solar panel capacity available for each building and the generated energy along the year according to the site location. The heloscope is an online software used to determine the solar panels required for each building, as shown in photos here. We conduct analysis for molar lab, health center, business automation, the central heating, and the IMT laboratory. There is a lot of spaces available for rooftop solar installation, as shown in the IMP laboratory and the health center, which is an potential for energy generation on campus. And here is an example for report generated from the heloscope modeling for each building, showing the capacity for solar panel could be installed in each building. For example, in the central heating building, it's around 77 kilowatt, and in the business innovation, it's around 19 kilowatt, and so for the other building. Also, it's showing the solar panel type used and capacity used, which is 1,339. And as shown in the blue trend, you can see the variation of the solar generation along the year. And it's clear that during the summer period, the solar generations is higher than the winter period. In the next step, we utilize the ReOpt modeling. The ReOpt is a web tool generated by NREL Transforming Energy. We did this simulation for the 31 building selected at Lehigh University to determine the storage battery according to each building load profile. After we make analysis with the heloscope modeling and having the load profile for each building, we were able to determine the storage battery available for each building, besides the energy generated from the solar panels along the year. Besides battery storage, we calculated the net present value for each site to see if it's feasible to install solar panel at this building or not. Besides, we calculated the greenhouse gas emissions reduction from solar panel installation. The trend here is generated from the ReOpt modeling, showing the PV generation, the building load profile, the PV charging, the periods when the PV charging the battery, the period when the grid charging the battery, and when the PV serving the load, as shown in different colors here. The blue table is a below table showing the climate action regarding to installing the rooftop solar. For example, for one building, the IMPT laboratory, there is a potential to reduce the emissions per year from 397 to 151 metric ton carbon dioxide per year. And on the right side, you can see the recommended battery storage for this building, besides the capacity of generation of the battery storage. Also, it's calculated the net present value along the years for this building, which showing a positive value, which means that this building have a good potential for installing the solar panel. This is only one example from the 31 building. In the next slide, I will show you the list of building with all calculations and the results. In this slide showing that after we collecting the data, added the data to the Dernel soft platform, and did the heloscope modeling to determine the solar panel, besides the ReOpt modeling to determine the battery storage required for each building. We list up and arrange all the distributed energy resources at Lehigh University. The table showing the building name, each building at Lehigh University, and the red building that the ones that add in this year during spring 24. The business as usual, showing the building performance without installing the solar panels. In the first column, we can see the energy consumed for each building from the grid, and the generator capacity as mentioned before by Ahmed, there is emergency generators attached to each building, which is not used in the last semester. We used it in participation in the demand response and calculated the revenue from participation by emergency generators. And the third column showing the greenhouse gas emissions according to the energy consumption for each building. For the 31 buildings, the total energy consumption is around 24 gigawatt hour per year. And the greenhouse gas emissions is around 18 metric ton carbon dioxide, 18,000 metric ton carbon dioxide per year. And the right part of the table showing the result after installing the solar panels and the batteries, which showing the financial and environmental impact from these installations. The first column here showing the capacity required or the capacity available at each building according to the space of the rooftop solar. The total available capacity for installing the solar panels around 3,400 kilowatt DC power, and the storage battery around 1 megawatt. 1 megawatt storage battery, and around 3 megawatt hour battery capacity. And for the average production for solar panels per year on campus, it's around 3 gigawatt hour. And there will be an impact, of course, in reduction of the energy consumed from the grid after installing the solar panels. And the column of the CO2 emissions showing that there is a total emission, there is a reduction in the total emissions to 14,000 metric ton carbon dioxide. And the last column showing the net present value for each building, which almost positive for most of building. Some of buildings are negative, which showing that it's not visible according to the solar installation and the battery installation to consider this building. And after listing up all the distributed energy resources, we start ranking the distributed energy resources according to some criteria. We have, as Ahmed mentioned before, in the breakdown instruction of the project, we did simulation for the distributed energy resources according to operational, environmental, and financial criteria to determine the best distributed energy resources for installation, and to determine if it's visible to participate with these distributed energy resources or not. For the operational side, we have 6 criteria. For the environmental side, we have 1 criteria only. For the financial side, we have also 1 criteria. By applying this tool, we can select the best distributed energy resources on campus. For operational, I will go fastly through the criteria. The first one is reflecting the ability of the distributed energy resources to decrease the energy consumption with the facility. The second one is looking for reducing the demand of the building, the peak demand. It's looking for the peak demand, not for the energy. The third one is looking for the grid exporting capacity. It's showing the ability of distributed energy resources to sell power to the grid. And the fourth one, looking for the resiliency of the building according to the battery installed and the solar panel installed. How much will be the building is depending on its own generation without the grid operation. And so for resiliency also, they are looking for the facility, how many hours could be the facility depending on its own generation during the outage of the power. For the self-sufficient index evaluation, it evaluates the capacity to generate sufficient energy to meet a significant portion. If you have a significant target to be achieved, it will be reflected by the self-sufficient index. For our project, we selected some of these criteria according to the project target, as Ahmed mentioned before. Sorry. We are targeting to participate in the demand response program. This is the first target. The second target, we are looking for environmental goals of Lehigh University to reduce the greenhouse gas emissions. And of course, any project should have a positive financial impact. So we selected 40% for operational criteria and 30% for the environmental and 30% for the financial. And from the operational subgroups, we selected the line load reduction 100% as because in our project we are seeking or we are looking for participation in the demand response program, which is mean the peak demand response reduction during the peak periods. And after using the DRR rating index tool, we now able to get the top 20 distributed energy resources rated according to this criteria. In the next slide, I show the top 20 site after sorting according to the previous criteria. It's showing that the first one showing the building name, and also the same as discussed before, how much energy generated before installing the solar panel, how much carbon dioxide emitted from each building, what is the proposed solar panel for installation, and what is the proposed battery storage for installation. And of course, the right side showing the financial and environmental impact from installing the solar panel according to the energy reduction for each building. The red highlighted items showing the potential sites found during the spring 2024. And also for distributed energy resources rating, the tool we used is already based on a neural network. The neural network is for their NetSoft team. It's a their NetSoft software, but as showing in the it's a machine learning algorithm. The neural network is a machine learning algorithm. According to the request criteria, you can select the best and the fit distributed energy resource according to this criteria. In the photo here, showing that the list of the distributed energy resources from the NetSoft neural network platform, and the selected skills is 40% for 40% for the operational side, and we select the load line reduction. And for the net present value, we put 30%, and for greenhouse gas emissions 30%. And according to this artificial intelligent neural network machine learning, we get the result from the NetSoft platform for the top 20 distributed energy resources at Lehigh University. And it's showing that the score for each building according to the input criteria. Until now, we selected the building, and we showed the potential at Lehigh University. And the second step is to participate in the demand response program. I will give a brief about the demand response program and why this is important. In the demand response program, we have two markets. One is the capacity market and another is the energy market. This slide showing the capacity market. The capacity market is the ability for the consumer to reduce the load at their location during the peak periods of demand, during the stress on the system, during the transmission line congestion, which means that when there is a high demand, the prices are going very high, and it will reflect in your capacity and transmission charges. As shown in the trend, the capacity and the transmission charges varies along the years. The yellow one showing the MAAC region. It's showing different region variation, and Lehigh University is located in the yellow one region. If we track this line, we can see it varies from 190 until 40%. So according, one of our goals from our project is to reduce the capacity and the transmission charging by participation in the demand response to achieve the minimum charges could be achieved. The energy market, it's a little bit different from the capacity market. The capacity market looking for big demand reduction, but the energy market looking for consumer reduction of load during the high prices period. There is published event from BGM showing that there is high prices during summer period. If you participate with your resources during this period, you can earn money. According to these steps, you can firstly sign up for the demand response program. You should track the electricity and demand surge, and you should participate in case of there is an extreme weather, which is reflected in the energy prices. The middle part showing that during the event, the consumer should reduce the load to gain money as a payback from this participation. Along our project, we did simulation for the both programs, the capacity market and the energy market, as will shown in the next slide. For the energy market, as I mentioned before, according to the extreme weather event, each consumer will face a high or will face an increase in the cost of the energy, as shown in this trend. This trend is showing the energy prices in last year. The red highlighted line is reflected to the prices in the real time prices, and there is a big potential to participate during these high peaks to gain money from this participation. As you can see, the prices could go up to 1,000 times of the normal price. The normal price is shown in the green line. So there is a big potential to participate in the energy market capacity, in the energy market demand response. And for the demand response, we simulated two scenarios, the economic demand response and the peak demand response. The first scenario is to curtail 1 megawatt hour from the big demand response of Lehigh University. The second one is to curtail 1.5 megawatt. As Ahmed mentioned in the first slide, Lehigh University peak demand around 14 to 15 megawatt hour during the hot summer period. For the economic demand response, we simulated 162 hours per year. And we found during the last year, the prices are going up in the 162 in this 162 hours. And as shown in the table, if we curtail 1 megawatt hour, we will reduce the greenhouse gas emissions with 114 metric ton carbon dioxide, and we will gain around $140,000 per year. Also, if we curtail 1.5 from the peak demand of Lehigh University, we can gain more from this participation up to $210,000 per year. Also, for the peak demand response, we are looking for participation in the both programs at the same time to have total revenue around $288,000 to $431,000 per year. And the last column shows that there is a greenhouse gas emission reductions from this participation during due to the energy consumption reduction from the grid. And finally, when we are talking about the result for the top 20 sites at Lehigh University, as mentioned before, we can earn money from participation in the demand response program. If we curtail 1 megawatt or if we curtail 1.5 megawatt, it will vary between $288,000 to $431,000. And from the energy generated on site from the distributed energy resources, we can reduce the energy or the electricity bills of the Lehigh University by $289,000 per year. And also, of course, by installing the solar on the rooftop building, we can reduce the greenhouse gas emissions by 2,000 metric ton carbon dioxide per year. And by implementing this project on campus, of course, it will increase the reliability and resiliency of the campus. For the future plan of this project, we are looking for a viability study to assess more technical and financial and environmental feasibility to determine the capex required for this project and the return on investment to give the stakeholders input to finance this project to be implemented at the Lehigh University. And this is our link resources. Thank you all. And this is the time for questions if anyone has any question. Thank you.
Okay.
Let's see.
Yeah. Questions for Mohammed and Ahmed?
I guess I could start with one.
Okay.
Okay.
Are you able to hear me?
Yes.
Okay, excellent. So great presentation. One of the things that sticks out is the diagram that you showed of many of the buildings with solar panels on them. They seem to be flat roofs and pretty significant. And as you provided the financial analysis, I don't know that I got a really good sense of the cost for the panels, and if these panels are going to be placed on the roof. Is there structural considerations that you have taken into account and included those costs if you were to place these panels? Because it's looking like a lot of panels. I'm thinking, quite a bit of weight. I don't know what the structural supports are for the roof. And are they able to just accommodate all of the panels that you've indicated they would go on?
Yes, good question. We discussed this point with the Lehigh University facility, and this is our future plan to determine the actual capital cost required for this installation on site to have a solid ground for this project. We only determine how much capacity could be generated from each building, but it needs more analysis for the building roof if it's applicable for installing the solar, what is the modifications required for the roof, if it needs some structure or something like this. This is the future plan for the project. The structural integrity of the buildings haven't been considered in this project. We only just evaluated the capacity of the roofs for each qualified building in order to simulate the capability of the campus for energy production. But the point of structural integrity hasn't been incorporated in this phase of the current project. This is for future works to include the structure. Is this,
okay.
Is this answering your question? Can you hear us well or not?
It's hard to hear.
Can you hear us well?
Yeah, I heard some of it. So just what I heard is basically that in the future, you would take into account the costs associated with any evaluation of the structural integrity or any sort of reinforcement. So
Exactly.
when you did the analysis, what costs did you use? Is it just did you use an installation cost, installation cost per panel, or just cost of the panels? What was used there?
The cost of the panels itself and the batteries, the material, and operational cost for the maintenance and the operation of the installation.
So no installation cost also?
No.
Okay. Yeah, just those are some of the things, if this is going to be a feasible option and you're going to take into account cost to do a real cost benefit analysis that you'd have to consider.
Yes, of course, that what we mentioned in the future plan, we are looking for more analysis for the project to determine the actual capex required for installation.
All right, thank you.
This is Revis. I did share Boris's questions about cost, so I appreciate that discussion. Good presentation. I just have a kind of a different question. Although you didn't look at cost in depth at this stage, but you did look at potential for the value of different installations. My question is, where was the highest sensitivity in your analysis? For example, assumptions were made about how many events in terms of energy reduction and demand reduction would be needed, and then based on that, calculations were done of savings in terms of energy and so on. Is that the most sensitive variable affecting the results of your analysis, or are there other variables that really were particularly sensitive to driving the outcomes?
So according to the distributed energy resources rating index tool, as I mentioned before, there is a weighted average you should put for this tool to determine the top sites available for the energy. According to this weight, we put 40%, 30%, 30%. According to this weighted average, you can select the best distributed energy resources on site. The most sensitive one is the operational. If you increase the percentage of the operational, it will be most sensitive. If you increase the environmental weight, it will be most sensitive. Did you get my point?
I think maybe we're talking on the same plane. I think maybe another way of phrasing my question would be, if, for example, the number of event hours in your assumptions were to decrease by 10%, how radically would that affect the energy, the total costs, the net present value of the total cost benefits? If it were only to change by 10%, it would go downward by 10%. Is it proportional? Is it a nonlinear relationship? I think the reason for my question, let me explain my motivation. I think in terms of this project, in terms of creating an insight and approach to how to do this for other facilities and institutions, the research will help define a systematic way to approach this. I think understanding that sensitivity is important. So if assumptions about those events are the key thing, or for example, the markets which establish prices for reduced energy or reduced demand, obviously those curves have a lot of volatility in them. If that volatility changes in a small way, will that have a very radical effect on the results, or is it a fairly proportional relationship? That's the general question I have.
Oh, can I speak?
Yeah.
Okay. Hey, Revis, let me interject. They didn't do a sensitivity analysis, but I think your comment is very appropriate. Which of the parameters that could most affect, your cost benefits and so on. I think this wasn't done though during this project.
I realize that probably wasn't done, and I certainly don't expect that. I was just wondering if there might be any first impressions that might have been formed in this initial effort. But yes, that plus obviously the comments earlier on cost would be key activities for future work.
And to, in connection with what Horace's question was too, the dynamic loading, the structural integrity of the roofs, all those are, we haven't done that. And that would surely be a concern, if we were to go forward. Any other questions for Ahmed and Mohammed? All right, so having no questions, let's go on to the next topic. It'll be Michael will be presenting on the blue economy.
Alrighty, can everybody hear me and see the presentation?
Yep.
I saw you speak, Susan, so I'm assuming that's a yes. So
I can hear it too.
Oh yeah, I guess I could.
Yep.
Alrighty, well, hey everyone, my name is Mike Perinato, and I'm also part of the Energy Systems Engineering Mastery Program here at Lehigh. And today, what I'm going to be talking about is the Powering the Blue Economy initiative, specifically how marine energy can help with water and energy systems for isolated coastal communities. And before I get started, I'd like to acknowledge my capstone advisor, Dr. Shalini Kishore, Dr. Rudy Shankar, and my research partner, Vaishnavi Kodapalli. So to kind of give an overview of what I'll be talking about today, we'll first start off about what the Powering the Blue Economy initiative is, give an overview of isolated coastal communities in the United States and desalination systems, Then I'll explain what marine energy is and how it can be harnessed. Talk about how I modeled my microgrid, how that microgrid performs. Then I'll go over the results and my future work. So to start, what is powering the blue economy? Well, the blue economy can be broadly defined as the sustainable use of ocean-based resources for economic development, improved livelihoods, and ocean ecosystem health. And there are many ocean industries that can fall within the blue economy, such as fishing, tourism, oil and gas extraction, to name just a few. And over the past few decades, there's been an increased demand for ocean-based resources, so these industries are growing pretty rapidly. In 2015, the global gross value added by ocean-based industries accounted for 1.5 trillion US dollars, which is roughly around 2.5% of the total gross global value added. And this is expected to continue and double by 2030. So in 2019, the United States Water Power Technologies Office created the Powering the Blue Economy Initiative. And this was done to further our development of ocean-based industries and emerging industries while maintaining our ocean ecosystem's health. And there are two sides of the blue economy: power at sea, which focuses on providing power at sea for offshore industries. And the second side focuses on improving the resilience of coastal communities, which is what I'm going to be focusing on today. So starting with the isolated coastal communities, overall, there are over 300 isolated residential communities across the United States. In addition to these residential communities, there are dozens of vacation resorts and coastal bases that all have to maintain their own power systems. Now, for the residential communities, we can see typical loads between 200 kilowatts and 5 megawatts per day. And for these communities, they all design their power systems with a primary focus on reliability over any other aspect. And so these communities typically use a diesel generator due to its high reliability. And while a diesel generator is really reliable, it may be hard to get diesel to these isolated communities. For example, in Bethel, Alaska, a fuel barge has to deliver around 13 million gallons of diesel fuel in the fall to last a community over the next 8 months. And for this community, since they have to get all this diesel at once, they have to build an extensive fuel storage system that also includes a refinery to help prevent spoiling during the later months. And due to these logistical issues, prices for energy can typically reach over $100 per kilowatt. So since a good portion of these communities are located in coastal areas, they have the capability to harness the unique marine energy resources that are close to them. And then I also wanted to explore desalination since it's part of the resilient coastal community side of the blue economy. And I also focused on it in my last semester's capstone. But most importantly, I explored it because of the growing rise in freshwater scarcity. Already, there are around 4 billion people globally that do not have access to reliable clean water year-round. And this number is expected to rise due to worsening climate change that is affecting precipitation volatility, reducing glacial areas, and contaminating groundwater sources. So when we can't get fresh water from nature, we have to start making it ourselves. And this can be done through desalination, which is the process of removing salt and other minerals from saline water. And there are two popular methods of desalination: thermal desalination and reverse osmosis. Thermal desalination was the most popular method over the past century, but more recently, there have been improvements in the energy efficiency of reverse osmosis technology, so it's becoming the more popular method. With the improvements in energy efficiency, the global capacity of reverse osmosis increased from 20 million cubic meters to 90 million cubic meters of water between 2000 and 2020. Now, reverse osmosis uses a semi-permeable membrane to separate the minerals from the water. With a large amount of pressure on the saline water side, it's able to pass through the semi-permeable membrane and leave fresh water on the other side. Overall, reverse osmosis can produce fresh water at a rate of 4 kilowatt hours per cubic meter. All right, so now kind of focusing on marine renewable energy. This is a map that shows the technical marine renewable energy potential in the United States. And overall, we can expect to harness around 2,300 terawatt hours a year if we completely capture this potential. And as you can see, there's a big difference in the marine renewable energy resource, depending on what region you're in. If we look at the West Coast, the primary resource is wave energy, and that's due to the large size of the Pacific Ocean. Waves are caused by the friction of wind across the ocean's surface, and since the Pacific Ocean has a large ocean surface, the wave heights become a lot greater than compared to other oceans. And this effect is seen more dramatically in Alaska, where the colder air temperatures are able to deposit more energy onto the relatively warmer ocean water. As we look at the Atlantic coast, we can see a more diversified mix of wave, ocean current, and thermal energy. And the latter two sources are caused primarily from the Gulf current, sending warmer water up to the north. And then scattered across the United States, you can also see that we have the potential to harness tidal energy, which in my opinion is the most interesting of the marine renewable energy resources because it's extremely predictable. Unlike solar, wind, or wave generation, tidal energy is dependent on the motion of the moon around the Earth. No matter what, we can expect there to be 2 high and 2 low tides per day. And after years of data and mathematics, we're able to predict how strong these tides are and when they're going to occur. So this gives us a reasonable prediction on how much energy is going to be held in the tidal resource at any point in the near future. Now, I've been talking about the potential to harness marine energy, but how do we actually do it? So continuing on with tidal, there's 2 primary methods that you can do to do this. The first method is to harness the energy from the tidal streams that occur in between high and low tides, utilizing a tidal turbine. And as in between the tides, the velocity of water flowing inland and then back out to sea increases. So as it passes through a turbine, it's able to generate electricity using a generator. The other method is to get energy from the height difference between high and low tides using a tidal barrage. So as it goes to high tide, water flows in through a tidal barrage through sluice gates. Right when you reach a peak of high tide, these sluice gates close, and then water can be slowly drained out through the turbine located at the bottom and released back out to sea. And then ocean thermal energy is kind of similar to how like a heat pump would operate. So there's a refrigerant, closed loop refrigerant, and warmer surface ocean water is used to evaporate this refrigerant. As this refrigerant vapor passes through a turbine, it turns the turbine, flows down into a condenser where colder seawater is pumped up, condensing the vapor back into a liquid, so the process can repeat. And then here on the bottom, you can see that there's a lot of ways we can harness the wave energy. Now, the GIF on the far left shows an oscillating water column, and this uses the wave heights to increase or decrease the air pressure inside of a chamber. As the air pressure increases, air is pushed out to the top of the chamber through a turbine, and as it decreases, air is pulled back in, turning the turbine again. Similar, the second one next to it shows an overtopping device where waves are allowed to overtop the device and fill a basin. At the bottom of the basin, there is a little channel where you can put in a turbine, and as the water drains out, it passes through the turbine, turning it and going back out to sea. Now, the next two, so the next two shows heaving wave energy converters, and this captures the vertical linear motion of ocean waves, and it converts the linear motion into angular motion using a power takeoff mechanism, which in turn can be used to power a generator. Similarly, the one on the far right shows a oscillating wave surge converter that captures the horizontal motion of ocean waves. And typically they're connected to a hydraulic piston, connected to a hydraulic generator that is able to generate electricity. And included with marine energy, I also wanted to explore offshore wind energy since it's located in the same region where we would be able to find the marine energy resources. Then over the past decade, offshore wind has been getting more attention due to higher, more consistent wind speeds offshore. In addition to that, turbines are also able to be constructed much larger offshore, increasing their rated capacities. Now, those both sound really good. However, it comes with a much larger cost than traditional onshore wind turbines. The table on the right kind of shows a general breakdown of the costs. So onshore wind costs approximately around $39 per megawatt hour, while a fixed offshore turbine would cost around $95, and a floating offshore turbine would cost around $145 per megawatt hour. And this is primarily coming from the balance of system capital expenditures, which are increased due to the extra prices that you have to use to construct the fixed substructure or the floating structure. In addition to that, you can also see the operational expenditures are double that than onshore wind for both the fixed and floating offshore wind turbines. Now, specifically, the two energy sources I wanted to explore were wave and wind resources because they are complementary. Since the wave heights are dependent on wind speed, as the wind speed is higher, it's able to deposit more energy along the ocean surface, thus increasing the wave heights and increasing the wave energy density potential. And as you can see on the chart, this is plotted for the month of February. Whenever you see a peak in the wind speeds, you can see that there's also a peak in the wave energy resource. You can see this happen for nearly every peak in wind speed throughout the month of February. All right, so now that we know the problem and a little bit about a possible solution, I'll talk about how I modeled my microgrid. So this microgrid is set up to provide power to a desalination plant, 2 pumps, and 40 4-person households. This microgrid will be located in Cape May, New Jersey, since Lehigh is working with the Atlantic Marine Energy Center on the Powering the Blue Economy initiative. So focusing on the energy system, as I just mentioned, the 2 renewable resources that were selected were wave and offshore wind. And to model how this system would work in an isolated setting, a backup diesel generator was used over a grid interconnection. In addition to the backup generator, an energy storage system was put in place with an unspecified capacity to see how the storage system would need to be sized for isolated grids with different contingency plans. Regarding the water system, there's one reverse osmosis plant that is used for the community, and that's going to be their sole source of water. Then there are 2 pumps. The first pump transports the water from the desalination plant to the community 5 kilometers away. And then the secondary pump is used to increase the pressure so that it can be used for residential use. So this graph shows the typical daily demand of the microgrid from the last slide. And as you can see, reverse osmosis takes up the vast majority of this demand. Now, this comes from how Americans love to use more water than any other country. And since we use more water, we have to pump up a lot more saline seawater and use a lot more energy to produce pressure and to get all this water to go through the semi-permeable membrane. The second highest demand is coming from the first pump, which transports the water to the community. And this is primarily because it has to be pumped a large distance. The second highest demand is the pump that increases the pressure throughout the community. And this is smaller since it's smaller than the first pump because it's transporting the water through a lesser amount of pipes throughout the community. And at the top, you can see the residential power demand. And this was modeled with the average household using approximately 40 kilowatts of energy per day, of power per day. And coincidentally, we can see that there's a correlation between water and energy use. So that fares well for plotting the demand. In the early morning while people are sleeping, not a lot of water is getting used and not a lot of people are using their electricity. But as people start to wake up and get ready for work, they're starting to take showers, using more water, turning on their lights, so you start to see a peak around 8 o'clock. It dips back down as people go to work, picks back up during lunchtime. There's a slight decrease until the kids come home from school around 3 o'clock. Dips again until around 8 in the evening, where you see the biggest peak, and then goes back down over the night. So now that we know the demand, we can start looking at the supply side of things more. And the wave energy converter that I wanted to explore was the RM3 floating oscillating wave converter, which can be seen on this side here. This shows a fixed one, but for a floating oscillating wave converter, these would be located higher to the surface and slightly below it, utilizing mooring techniques. But overall, the way you can calculate the wave energy resource for a certain region is by using these constants here, the density of water times gravity squared over 64 pi, which is roughly around 0.5 kilowatts. And then the wave energy resource is more dependent on the significant wave height squared and the period. Now, the power matrix on the right shows the power output of the ARM3 wave energy converter. And this converter has a peak capacity of around 360 kilowatts per device, which occurs at wave heights greater than 4.5 meters and wave periods greater than 5.5 seconds. And the way I source the data for wave heights and periods is I found a local data buoy located approximately 30 miles offshore of Cape May that has hourly data on significant wave heights and periods. And then I developed a code that matches that hourly data to the values in the power matrix to get hourly power output for the month of February. Now, turning our attention back to offshore wind, I chose to look into the GE 1.5 SL wind turbine. Now, this turbine is typically used on land, but I chose to go with this model because most offshore wind turbines are already rated at around 6 megawatts. Which, using a turbine of that size, you would only really need one turbine to help meet the demand. So I chose to go with the smaller model to kind of paint how a mix of wave and wind energy can be used for the microgrid. But nonetheless, the graph here shows the power curve for the GE 1.5 SL turbine. It's rated at 1.5 megawatts ideally, assuming there's no losses. And that can be seen with the black line here. It has a cut-in speed of that occurs at 3 meters per second, and then reaches its rated speed between 12 meters per second all the way up to 25 meters per second, and that where it reaches its cutout speed and stops producing electricity. Now, the black line shows the ideal power output without losses, but the dotted line shows a more realistic output after assuming around 8.5% of losses due to soiling, availability, and performance. And then similar to the wave energy, I also got hourly data for the month of February on wind speeds from the same data buoy and use this power curve to figure out what we could expect from an offshore wind farm. So the first microgrid that I tested was a microgrid that was powered primarily with the offshore wind farm as the sole renewable energy source. So this farm consisted of 4 of the model turbines, which resulted in a total farm capacity of around 6 megawatts. I then tested this setup on 3 different days: a low generation day, average generation day, and high generation day. So looking at the low generation day, we can expect to see wind speeds around 0 to 5 meters per second. And on days like this, we don't really expect to see a lot of wind generation, and we have to rely on most of the diesel generator for most of the day. Overall, the wind farm is able to recover around 21% of the daily electrical demand on days of low generation. Looking at the average generation day, you can see much better performance where there are wind speeds of between 5 to 10 meters per second. And here we can see that there is no reliance on the diesel generator, since there's an excess amount of energy produced in the early morning hours that can be going towards the energy storage system. While the energy generated by the offshore wind farm may not be enough alone to reach the demand, the excess energy stored is able to help meet the demand throughout the day. And overall, on the average day of generation, you could expect the wind farm to produce 113% of the daily electrical demand. Now, looking at the high generation day, you of course would get to see the best performance. And on these types of days, you'll see wind speeds greater than 10 meters per second, where the turbine is able to reach its rated capacity at some points throughout the day. And similar to the average day of generation, you see an excess amount of power generated in the early morning hours, and to a lesser extent in the middle of the day. And since the wind farm is producing more energy, you're able to store more energy without having the need of discharging it. So this energy can be used to help maybe on, say, the next day would be a low generation day. you can discharge that energy for the day after that. Overall, on days of high generation, you can expect the wind farm to produce 138% of the daily electrical demand with no reliance on the diesel generator. And the second microgrid setup that I tested focused on utilizing a wave energy converter farm as the sole renewable energy source. And similar to the wind microgrid, the wave energy converter farm is rated at 6.1 megawatts. The extra 0.1 comes from the uneven sizing of the individual capacity factors between the wave energy converter device and the wind turbine. But nonetheless, we can see the performance on load generation similar to what we would see for the wind microgrid. You can see wave heights range from 0.25 to 1 meters and periods range from 3 to 5 seconds. When on days like this, we can expect the wave energy converter farm to produce 5.3% of the daily electrical demand. So for most of the day, we have to rely on the diesel generator. On the average generation day, you can see slightly better performance, but it's not the greatest. Here, you would expect to see wave heights ranging from 0.75 to 1.5 meters with a similar range of wave periods. There's a little bit of excess power generated during the early morning. However, this is quickly discharged by the energy storage system to help meet the first peak. Then after that, you have to rely on the diesel generator for most of the day. Overall, on a day of average generation, you can expect to see around 30%, the wave farm produce around 30% of the daily electrical load. Then on the day of high generation, you get to see much better performance. Here, wave heights are generally greater than 1.5 meters, and there's a slightly larger range of wave periods of between 3.5 to 6 seconds. And then similar to what we saw in the average day generation, there's an excess amount of power produced in the early morning hours when the demand is low. And this can go towards charging the energy storage system, which is able to help meet most of the day's demand up until around 3 o'clock, where we have to start utilizing the backup diesel generator to help meet demand for the rest of the day. But overall, on the days of high generation, you can expect the wave energy converter farm to produce around 78% of the daily electrical load. So the last microgrid setup that I tested was a mix of wave and wind. The wind farm was rated at 3 megawatts, and the wave energy converter farm was rated at 3.2 megawatts. And then similar to the last two slides, you don't really see a lot of power produced on a low generation day, where this mixed farm is able to account for around 13% of the daily electrical demand, and the diesel generators are going to have to be operating for most of the day. On the day of average generation, you see slightly better performance. There's a period in the early morning where you're generating excess power that goes towards the energy storage system, which is able to help meet the first peak in demand. However, as we get to our lunchtime, the power stored is used up, and we have to start relying on the diesel generator again. And you'll see that trend for the rest of the day up until like around the late evening for this model day, where you can start to see that the mixed farm is able to produce enough energy to meet the demand around 11 and 12 o'clock. Overall, on this type of day, you can see that the mixed wave farm would be able to produce around 70% of the daily electrical load. And then on days of high generation, you get to see the best performance for the mixed model. Again, you have the excess power generated in the early morning that goes towards the energy storage system. There's a little bit of excess power generated after the first peak, but overall, since there's enough excess power generated in the early morning, this can be used to charge the energy storage system throughout the day, and there's no reliance on the diesel generator. And the mixed wave and wind farm are able to produce around 105% of the daily electrical demand on these types of days. Now, I've been talking about energy storage systems a lot for all those performances, but how do we have to size these? Well, that's primarily on what the community would want to have as their contingency plan. If you want a 50% contingency plan and not rely on diesel generation as much, you would want to store around 25,000 kilowatt hours of electricity. And then similar for the 100% contingency plan, if you want a full day covered, you need around 50,000 kilowatt hours. And for 2 days, you need 100,000. Now, the rated power of these batteries can vary widely based on the community needs as well. If you would want the energy storage system to provide half the load throughout the day, you would want it to be rated at around 1 to 2.5 megawatt hours. However, if you want it to be more reliable, more dependent on the renewable resources, you would want this rated at 5 megawatts to help meet the evening peak demand. But what types of energy storage can we use for isolated microgrids? Well, if you're looking at an island community where there may not be a lot of space to develop a large-scale energy system, battery storage may be the way to go. But if we're looking at the Alaskan communities where there's a lot more land to work with, we can maybe develop a pumped hydro storage system. And this would be really useful for these communities, since it would be able to, if you have a long period of high generation and then a long period of low generation, you're able to store a large amount of power that can be discharged whenever you need it. However, this pumped hydro system would probably not fare as well for the northern Alaskan communities at the higher latitudes and around the Arctic, because pumped hydro does not work well when the water is frozen. So we might be wanting to look into a compressed air storage system. And this has another benefit for the northern communities, because when you compress the air, you also generate a lot of waste heat, which can be used to go into heating all the residential or other buildings throughout the community, which would decrease the overall electric demand. And I know that was a lot of information at once since I was trying to cover all my bases, so I'll try to wrap it up in this slide. So as we saw with the different performances of the microgrid, it can clearly be seen that offshore wind energy is a much better option to go with if you're looking at the Atlantic coast specifically. I modeled the 2 farms in NREL, the SAM tool, which found the capacity factor for the offshore wind farm to be around 35%, and the capacity factor for the wave farm to be 13%. But then again, marine energy varies from region to region. If we're looking at the West Coast, wave energy may be cheaper than offshore wind energy. For one, the wave heights are greater, so it's going to be having a higher capacity factor. And 2, if you want to construct an offshore wind farm along the West Coast, they would all have to be floating turbines due to the greater ocean depth. And then you can start to see the same thing in Alaska, where it's mostly on wave energy, but they also have to see the greatest tidal speeds and height ranges in the United States. So you can also, there's a lot of potential to harness energy there. If you're looking at Hawaii, they have a great near 50-50 mix of wave and ocean thermal energy conversion. And these both can be combined. However, ocean thermal may be better for Hawaii since they have higher, more consistent ocean temperatures year round, and there's not much fluctuations in the temperature around the year. So that concludes kind of what I wanted to cover today. So I'll be talking about the future work that I'm planning on doing. So at the beginning of the semester, my research partner and I wanted to develop an optimization model that optimizes the scheduling and operational costs of the energy storage systems. And we're nearly done with that. I'd say we're 85% completed with the optimization model. We just have to go back and tweak some of the electrical demand side of things for the water system. Well, then after we finish that and get our results, we plan on developing an energy storage decision-making model. But that kind of wraps up what I wanted to talk about. So I'm open to any questions.
Questions for,
I should probably unmute it. Let me mute this.
questions for Michael?
Well, this is Revis. I do have a question. Michael, you did look in depth, obviously, at the capabilities and potential for the different resources and considering their geographic location and so on. I was wondering, and I thought it was really interesting, by the way, when you took into consideration the geographical limitations, for example, compressed energy storage and waste heat as a district heating resource. What I was wondering is, have you gotten to, or do you plan to get to, looking at integrating the capital cost differential in these different mixes in order to see if that affects what's optimal for a particular location, or is that on the horizon in future work?
I would say including the capital costs are more like later on the horizon. From the research I found, like from this semester and last semester, a lot of the marine energy technologies are relatively new. So there's going to be a much more dramatic cost than traditional like offshore wind energy. So what we wanted to focus on was just kind of modeling the operational sides of things, the operational costs to better paint like how this would work in the future. Because from what I've found in the papers that I'll develop like a wave wind farm, they all kind of come to the general conclusion that the wind farm is going to be cheaper than the wave, just with the current limitations on the technology.
One quick follow-up: do those general conclusions take into consideration, you know, transmission infrastructure and other sort of peripheral considerations?
Well, yeah.
Or is that a relatively unexplored area so far?
Well, I did see some papers that explored the transmissions of a mixed wave in a wind farm, but they're typically like combined, like they're going to be located in the same place. Like in between the wind turbines, you would have the wave energy converters, and it's more optimal to do it that way since you can kind of combine like both of those types of devices can use the same transmission lines to send it all back to shore. But there's not really too much information right now on I didn't really look too much into the information on like the transmission of the energy back to the shore. So
that's fine. I was just curious. I appreciate it. Thank you.
yeah, no problem.
Still have time for one, Horace?
I'll ask one quick one, and this is just out of curiosity. One of the slides you showed the dropout speed of the wind turbine, and being that the system that one of the hybrids you looked at was wind and wave, my question is there a coincidental potential wave scenario that would coincide with the dropout of the wind turbines? So basically what I'm saying is that you would lose if you had a hybrid system where you're using wind and wave. Is there limitations where the wind, because of the height of the wind, of the waves from the winds, would drop out, or it continues to generate?
So you're asking, would there be like a point in time where, like, if you like reach the 25 meters per second and the turbine stops producing electricity, would the wave farm still be able to produce energy?
Yes. Or
yeah,
is there a sense of when, or limitations as to when the waveform would not be able to produce energy? Obviously, if there's no waves, that's not what I'm talking about.
Yeah, definitely. So yeah, as you can see on the power matrix, like you basically need wave periods of greater than 3.5 seconds for all that, which happens most of the time. You barely ever see it go below 3 seconds. And then you also like you start to see like it stops producing energy at wave periods greater than 20.5 seconds, but it typically never reaches that in at least the region I explored. If it does, that's probably due to some extreme storm conditions. But even at like the higher wave heights, you can still see the wave energy converter producing a lot of energy, like still reaching its rated capacity. So like at speeds of 25 meters per second, we might be reaching wave heights and periods around this area right here. So that we'll see some wave, like you'll still see some energy production from the wave farm, but no energy production from the wind. But then again, the offshore wind speed typically doesn't reach that high of a velocity unless there's like an extreme storm condition happening, like a hurricane or something.
All right, thank you.
Yep, no problem.
Rudy, this is Jim Robinson. I have one other question after this one. part of the issue regarding the cost is critical, and a lot of the work has been done to compute the capacity factors and so forth. There's a flip side. Rather than spend all the time computing the installation cost and operating cost, there's a flip side way of addressing that, possibly in another project, to determine the cost that is offset due to less diesel and less carbon credits. Just having that cost information of what the offset would be for both operating cost and cents per kWh and carbon credits would be a useful next project to get a handle on how big the government rebates would need to be for installation and how much the ongoing subsidy would need to be to make it competitive compared to diesel.
Yeah, like, so I would see, like, a lot of these communities are more focused on reliability over like anything else, because they have to have the essential societal functions, like operating like wastewater treatment. So there is a potential to get some subsides through like reduced use of carbon. However, I think they're going to be more focused on like still having that backup diesel generator there just in case there's like a very long period of intermittency or something happens to the offshore renewable farm.
Thank you very much.
All right, there are no more questions. We'll have Alex make his presentation.
Enable screen sharing.
All right.
Rudy, doesn't Alex need to be a co-host? I don't have that ability to make him a co-host. You have to do it.
You can go to the corner like where your camera is, and then go to the dots. Oh. All right, sweet.
Okay, I just fixed it. I reclaimed the host and I added Alex as a co-host. So you should be able to share the screen now.
Thank you. All right, good afternoon, everybody. I'm Alex Romanowski, and today I'm going to be talking about the viability of net zero multifamily homes across the United States. I'd like to take the time to thank David Bruns from the Bruns Realty Group, my sponsor, Dr. Shankar, and a number of other folks who helped me along the way for this project. Just going to give you a quick overview of what I did this year. First, I studied a series of net zero market rate apartments in upstate New York and learned the technical and financial elements of the project. They were able to recoup the cost of going green by bundling the market value of utilities and rent. And then due to their energy efficiency improvements and on-site energy generation through solar, they paid significantly less for utilities than what they charged. And they adjusted their design for different climate zones across the United States. I adjusted the design across the United States and modeled all the energy consumption. Then I was able to determine the net value of the utility fee versus the cost to build green. And I found that the best financial results were in climate zone 5A. So essentially, it's financially viable today just using the market rate of utilities and federal incentives to build net zero in climate zone 5A. Now onto the agenda. We start off with climate change and the reason why, go over overview for semester 1, then jump right into semester 2 and applying the lessons I learned, and then get into the modeling and the financial analysis for this project. First, I'd like to introduce myself a little bit further. I'm a master's student studying energy systems engineering. I got my undergrad from Lehigh as well in integrated business and engineering and finance. I had a minor in mechanics and materials. I've been working for 2 years now for Active Solar Development on their land team. And I also spent a summer in New Jersey interning with D.R. Horton on their land team. Climate change and the reason why. This is the United States at 10 feet of sea level rise projected by NOAA. And you can see the future sea level in that lighter blue with the existing sea level in that darker blue. And this is slated for around 2060, 2080 at 1.5 degrees C of global temperature rise. And, you know, part of the big driver behind my desire for helping out with the climate crisis is that's where I live. And it's currently underwater, you know, it may be underwater in the future. And then my favorite place on earth, Florida Keys, will also be underwater. Fortunately, I like to scuba dive. Unfortunately, I'd like to visit my house without a mask and snorkel on. But you know, I grew up hunting, fishing, pretty much anything outdoors, camping, you name it. And I've been reading all these projections about, you know, just devastating climate impact to nature, our wildlife, speciation. And I want to watch my kids and my grandkids grow up and enjoy nature as much as I have. So that's my big driver behind trying to enter the sustainability space. And, you know, we're running out of time to be able to actually turn the ship around. So on the left, you'll see a graph from the IPCC giving us our budget until we surpass 1.5 degrees C and 2 degrees C. And it looks like, you know, we've only got until 2026. So it's more than likely that we're going to surpass both 1.5 and 2 degrees C. Now, on the right, you'll see a UN emissions gap report of 2022, highlighting how policy is going to be able to impact the amount of carbon that we're emitting and what we're going to need to do to stay within the bounds that we've set. And it looks like, you know, we need to make a lot of change. So what happens if we miss? Well, there's all sorts of analysis with ranging, you know, levels of impact, but this one in particular took natural disasters as a function of GDP loss and then scaled it logarithmically along with global warming temperatures. And we can see that as the planet gets hotter, we're likely to see more devastating natural disasters that are going to impact our GDP. Now, you know, the accuracy of any of these forecasts, I don't know. I'd rather just not roll the dice. So what can we do now to help avoid that situation? Well, this carbon emissions is taken from the IEA in 2022, and we can see that building operations contribute to 27% of annual CO2 emissions, and the construction industry and other construction also significantly contributes to CO2 emissions. So if we start building clean, we can reduce our carbon emissions. And that's why I'm a big proponent of building net zero, which is when your annual energy consumption is equal to your energy production. And there are a lot of benefits surrounding net zero. I'm going to spend a lot of time focusing on the financial aspect in this presentation, but I want to spend a little bit of time to highlight just how comfortable these buildings are, because they've got airtight envelopes, and they're very thermally well insulated and sealed. They're super resilient. If you're going to have power outages, a lot of these buildings have passive heating and cooling fixtures built into them. Obviously, they're eco-friendly because they see a significant amount of energy savings, and they're better for the grid. These buildings have a lot of building management systems, and they can really tailor their energy usage around when their energy consumption is, and what the grid's needs are. That's a little bit further down in the future. But focusing in on the purpose for this project. First semester, I wanted to understand the financial and technical challenges of net zero building. And this semester, I worked to identify the most viable states for net zero development outside of New York. Quick recap of semester one's work. How did I get here in the first place? So this picture was taken on top of Solara's roof. It's a solar thermal installation I did for a pool system. Quick Google search, looking for work over the summer, and a couple of phone calls later, and I ended up on this roof doing some solar thermal installations, and I just thought the project was awesome for both Solara and net zero as a whole. These are some of New York's first market rate multifamily net zero apartment complexes. And I had been studying this stuff for a while, and it was just all the technology that I'd been, reading and listening, watching, just all in one. And it was actually, financially viable, which is really exciting to me. So naturally, I had three questions when I started working at Solara. First of which was, how are these projects all market rate, net zero, yet still financially viable? Because that's something that I'd continually been told time and time again is super high efficiency building just isn't quite there yet. We need the cost to come down. And why isn't this done everywhere? I spent a lot of time last semester talking to folks in industry and trying to understand some of the bigger issues with these projects. And then this semester, if it doesn't work everywhere, where does it work? Now we go into some of the basic technical elements of net zero building. The first semester's presentation goes a lot more in depth, especially into Solara specifically. Let's just do a quick review. So the first is the envelope. You want to make sure that your envelope is airtight. That way you're not losing any air to the outside, and there's no infiltration inside. The next, you're going to focus on very heavy insulation and high performance windows and doors. So that way you're keeping your conditioned space thermally insulated from the outdoors. After that, you have to bring in fresh air because these buildings are so airtight that you need some mechanical ventilation to keep the building healthy on the inside. And then now that you've got such a thermally insulated building, you can really downsize a lot of your heating, cooling elements, and just add in high efficiency appliances as well. This will decrease the building load. And then on top of that, you pair that with an energy management system that's going to fine tune all of your systems to make sure that they're working at the highest efficiency possible. And then you throw renewable generation on top of that, and it'll really, offset your building consumption. A little bit more about Solara. This project was 11 buildings, 248 units, a 3-story multifamily luxury apartment complex. They've got an elevator, a lot of very nice amenities, and higher finishes. And other than being net zero, what's unique about Solara is the way that they ran their financial structure. So on the left of this graph, you'll see traditional apartment complex, and then on the right is Solara. With the traditional apartment complex, your landlord is just charging for rent. With Solara, you've got rent, utilities, cable, Wi-Fi, and a ton of other amenities all bundled into one fee. And the reason why they do this is to recoup on their energy efficiency improvements. So the owner's paying significantly less utilities than the market rate, so they're able to capture some increased operating income. This will help cover the increased capital for the green investment. Now looking into Solara's financials, we've got the monthly utility fee less the residual bill will give you their monthly and annual NOI from that utility fee. And then evaluating that at a 5.5% cap rate, you're left with a utility disposition value of almost $34,000. Now compare this to the green cost, you're about equal. And this is for phase 3. We'll get into why that was a little bit more expensive later. But then looking at your net disposition value, upstate New York had a ton of incentives. This is on a per unit basis. So the increased value of building green for phase 3 of this project was $21,000. And now that we understand a little bit more of the technical and financial aspects behind net zero building in upstate New York, it's time to apply that to the rest of the country. And first step in that is going to be state selection. So how do we know which states to look at? First thing we're going to do is break the country up by climate zone. And then we're going to look at the states with the highest utility rates in each of those climate zones, and then cross-check the solar policy to ensure that it's going to be friendly towards net zero development. Starting with the climate zone, the country is broken up into all of these different zones. The first one that I examined was 3A down south, and then the rest were 4A, the 4s, 5s, and 6s. The reason why I left out some of the very humid or very cold climates is because those are just going to be more extreme, and the modeling that I was using is a little bit more limited for dehumidification and some other things. Now, the design elements are relatively similar for the climates circled in red compared to that in blue. And some of the differences between zone 3 and zones 4 through 6 are around the insulation. As you get colder winters, you need significantly more insulation. Your heat pump efficiencies are going to degrade in the colder climates. And you also need to change your performance standards of your windows and doors to allow for more solar gain in the north, where you want your windows to be more tinted down south to prevent that solar heat from entering the home, because you're in a predominantly heat intensive environment. And finally, you've got your under the slab insulation is going to change a little bit based on what climate you're in. Now, looking at the utility rates, I got average utility bills from Forbes all across the states. And these are the states in each climate zone that had the highest utility bill. If you're bad at geography like me, those are Georgia, Nevada, Wyoming, Kentucky, Maine, and Connecticut. Now, I cross-checked with the solar policies, and Kentucky and Georgia were actually not going to be favorable. So I had to switch to Arizona Arkansas and Maryland. And you can see, between Georgia and Arkansas, that's a pretty significant difference in the monthly value of the utility bill. So as we're trying to, chase down this value of the utility bill, it gets a whole lot harder to make these projects pencil when that monthly value goes lower. Now, going to get into a little bit more of how solar policy varies by state, but first going to lead you on with a few key terms. Net metering is the balance between energy production and energy consumption over a period of time. A lot of states vary based on the time frames in which they include net metering. And then states also vary based on your net excess generation. So this is when you're producing more than you consume in your metered period. And most of the states at this point are going to be reimbursing you at the avoided cost of energy, which is different than the retail rate. The retail rate is the dollar per kilowatt hour figure that you're going to see on your utility bill, where the avoided cost is what the utility is paying for that energy. So it's going to be a fraction of the retail rate. And the final term are SRECs, or solar renewable energy credits. And these SRECs can be sold in some states on a market. They are generated per every megawatt hour of energy produced. And then companies will buy these to offset their carbon emissions. And essentially, it's just a way for the government to incentivize the renewable industry. And it definitely helps out the financials. So now that we've got those terms under our belt, we're going to look at the different types of net metering policies. The first of which is annual reconciliation. So typically when you think of net metering, this is going to be what most people are used to. And this is the annual consumption versus production. So in orange and yellow, we'll see the production of the building relative to its energy consumption over the course of the year. If they equal out, your kilowatt hour charge for that building is going to be 0. Next is going to be your monthly reconciliation. So instead of summing everything up annually, you just do it per month. In the summer months, you'd be expected to have net excess generation, which is going to be reimbursed at the avoided cost of electricity. So, that much lower value relative to in your winter months, you're not going to be producing as much. So you're going to be paying that full retail rate. This really harms the economics of a solar project just because of the seasonal variation in production. The next, which is more stringent, is time of use reconciliation. So on this chart, you can see the solar generation curve in red and the load curve of the building in blue. Obviously, solar is peaking in the middle of the day, and the load curve doesn't always follow that. So utilities chunk up these times of days into various rate categories. So in the early morning, your super off-peak is going to be your cheapest electricity. And then when your solar's high, and in the late evening will be your normal off-peak. And then right when everyone's getting home from work is going to be your peak pricing. Now, how this works is they take those different chunks and then they net meter over the course of a month. So what you would have is in your super off-peak, you're not producing any solar, but you're also not going to be consuming that much. During your off-peak, you will probably have net excess generation, which will be, again, compensated at the avoided cost. And then during your peak hours, you're going to have, be paying the retail rate. So there's some things that you can do to shift your building consumption towards when your solar production is. But again, this is just a lot harder to pencil than traditional net metering. And then the least solar friendly would be net billing. This is when anytime you're sending electrons into the grid instead of consuming them, you're immediately compensated at the avoided cost of energy. So 3 cents a kilowatt hour, compared to maybe 13 cents a kilowatt hour. And this is where, battery storage systems would start to make sense if they were more affordable. Okay, so that was a lot, but how does it all translate in terms of the United States? Well, in green, we have states that are net metered annually. And of those states, the ones with the asterisks have a SREC market. So that's going to be increasingly more financially viable just because you can sell those SRECs. And then your blue states are going to have net metering monthly with your compensation for excess generation at the avoided cost. This is definitely going to hinder the returns for solar. And then your tan states are net building. That's going to be pretty tough. And then there's some states that are switching to time of use, mostly the Carolinas. Some states are regulated by utility instead of a statewide mandate. And then California and Texas are just overall complicated. So for the sake of this, we're going to run from those. All right. So we understand which states we want to target based on our climate zones, our utility data, and our net metering policies. It's time to model the buildings and understand what our building consumption is. This is the methodology for modeling. I took the International Energy Conservation Codes by climate zone, and those are going to basically, guide you in the direction of what you want for all of your insulation values and various building components. And then Solar's design and the climate data go into this passive house planning package. This is essentially just this monster Excel sheet, which is industry standard for being able to model energy consumption for high efficiency projects. And then from there, your output, your total consumption, and using PV watts for solar carports, I modeled the system size that I would need per geographic location to offset the total consumption. This is a cool chart that comes out of the passive house planning package. I believe this was for one of the southern states as far as heating demand. The gray is the mechanical heating that you would need, where yellow is from solar gains and internal heat gains, and then the blue is your sum of losses. So as you can see, towards the summer, you're going to be actually gaining heat back into the building, so that's when you'll need cooling. I would also like to point out solar radiation. So the dark red means that your panels are going to be a lot more efficient. We've heard this all the time that California, Arizona, New Mexico, Nevada are great for solar, and the Northeast, not so much. So this will actually impact the economics of the deal and your efficiencies somewhat. Now for the modeling results, we've got state, climate classification, how much energy the buildings are consuming a year, your solar efficiency. So for every kilowatt of power, how much energy are you generating over the course of that year? And then your solar size. I'd like to point out Maryland and Nevada. Nevada's got a lot more energy consumption than Maryland because it's a more demanding climate, yet its solar efficiency is significantly higher. So its solar system size is actually smaller than Maryland's. And along that same vein, Maine and Wyoming have similar energy consumptions, yet Wyoming's efficiency is better. So the system size is smaller. All right. So we've got our annual energy consumption and our solar system size. It's time to see how much this actually costs to build and if any of it's going to pencil. This is one of the main equations that I used to drive what inputs I needed. You find the value of the utility less what it costs to build green, and that's going to give you your net value. Is it positive or is it negative? And that green cost is a function of, you know, your net zero building cost less the cost to build the code, plus your solar installations minus any federal incentives. Starting off with your net zero cost, I had two different sets of cost data, both from Solara. First is phase 1 and the second is phase 3. In last semester's presentation, I talked in great depth about the technical differences between the two, but we're just going to touch on those. Phase 1 was built to be net zero, but phase 3 was more ambitious with net zero and carbon sequestration in line. So for phase 1, you know, just 2x6 exterior walls and spray foam for the insulation. With phase 3, they wanted to sequester carbon within the walls. So they switched to cellulose insulation, need a bigger wall because its R value per inch is lower. And then they had to vent the attic on the flat roof to allow for blown cellulose instead of using foam. All of these were significantly expensive. And when comparing to building costs in other states, building the code, it's not viable without incentives, which is a shame because obviously adding carbon sequestration into a project is going to be the best for the environment. But that's just not where we are today as far as financial viability. Additionally, solar hot water is no longer financially viable. The incentives dried up and photovoltaics also got significantly less expensive. So it's now more cost effective to pair PV with an air to water heat pump and electric resistance hot water heater than also adding solar hot water on top of that. Now, looking at Nevada specifically, these are all the line items that contribute to energy efficiency. And we've got Solara's cost data. I had to put it into today's dollars, adjusting for construction inflation. And then I was able to pull costs from a national home builder. They do 3-story multifamily walk-up apartment units. So not completely apples to apples as far as the finishes, but as far as the building framing, it's going to be pretty comparable. Now, looking in the far right-hand column is the difference. We're going to go through some of these. So we can see that net zero building is incredibly more expensive in terms of your HVAC. This is in dollars per square foot. So the reason for that is the energy ventilation units. For all of the mechanical air ventilation, that doesn't exist in code buildings because they aren't so airtight that the buildings don't breathe. The electrical was also a little bit more expensive. I believe some of this is due to regional cost differences, but also Solara's got a very robust building management system and a lot of other electrical systems. Then the doors, insulation, appliances, windows, and hot water, you're basically building everything to be super high efficiency, so that usually costs more. Now, one interesting thing to note, all the way at the bottom is the plumbing saved money. Some of this could be regional, but on top of that, the engineers that designed the building practiced high efficiency plumbing. So just making all the lines more compact, and that saved money right off the bat. So your total cost difference is $14.40 per square foot. Now, what incentives played into this project? I wanted to stay away from any sort of state incentives or utility incentives because those change really rapidly. But with the Inflation Reduction Act, we have a couple of incentives that are going to be here to stay for a while, and developers can rely on those. First of which is your photovoltaic investment tax credit. It's got a 30% system cost, along with a 10% adder if you buy products made in the United States. And then there's the Department of Energy's Zero Energy Ready Home incentive, which is $1,000 a unit for multifamily, or $5,000 a unit if you build with prevailing wage. Personally, I'm not well versed enough in prevailing wage to be able to anticipate increased labor costs across different markets. So I just stuck with the $1,000 a unit and the 30% ITC. Now, financial results to get the disposition value. Let's focus on Arkansas and Connecticut here. We've got our monthly utility fee and the residual utility bill. Because Arkansas is reconciled on a monthly basis for net metering, their residual utility bill is significantly higher. And you can see that your annual utility NOI is going to be way lower in Arkansas. Now, looking at the green costs, it's a lot cheaper per square foot to build down south net zero because the requirements are a lot less demanding as far as the climate. And then all the way on the right, you've got your green cost per unit. Now, moving over to the equation I showed you earlier, you're going to take your annual utility income and evaluate that at a 5.5% cap rate, along with your green cost per unit, and that's going to give you your net disposition value. So for Connecticut, we can see that over the life of the project, it's worth $35,682. And then Maine and Maryland are also up there as far as some of the higher disposition values. Now, applying based on each climate zone, I took the residual utility bill of the individual state that I looked at, applied that to the climate zone, along with the cost per square foot, both on the building basis and the solar basis, because climate zones usually have similar radiation, as well as the annual energy consumption. And then all of these factors, I took all those factors and calculated the disposition value of building green for these states. What we can see is that green is the most favorable with over $20,000 of additional value per unit, where blue is between $15,000 to $20,000. And, that's about where your viability starts to drop off. And then anything less than 10K is going to be really rough. And we see that a lot of those states that are not viable are due to monthly reconciliation of solar or straight up avoided cost or time of use. So you really need annual net metering to be able to pencil this. And then I didn't examine the West Coast much because they've got a whole lot of regulation around building, but it's likely viable given how many projects take place over there and how stringent their existing codes are. Now, looking at cashback and IRR, let's focus in on Connecticut, Maine, and Maryland because those are the most promising. We've got our green cost and annual utility net operating income that I pulled from the other tables. And then assuming a 80% construction loan at a 7% interest rate, you've got your annual debt service, and that yields your annual profit per each green improvement. And then 20% cash equity, taking your profit and trying to find your cashback period on cash that you invested in a project. You're going to see for Connecticut, you're at just under 3.5 years, which is crazy for energy efficiency. And an IRR, I did scale all of the utility bills at 1%, which might be a little conservative, but your IRR for Connecticut is huge at 43%. And then Maine and Maryland are a little bit more standard as far as IRR is concerned, and the cashback period is longer. But it's super exciting to see that there's, states outside of New York that are not only have a positive and high net disposition value, but also realistic cashback and internal rate of return. Going again to another heat map of payback period, we can see that it's pretty much just the Northeast is going to have a reasonable payback period, with green of less than 4 years, blue between 4 and 6, and that tan between 6 to 8. It's worth saying that some of the states that are in the 8+ year range are probably more viable. I think a lot of these estimates are conservative. And now on to some additional considerations. First of which is time of use and demand reduction. Solar is engaged with their local utility on a demand reduction project, and they believe that they can get 20 to 30% of their peak demand reduced for 4 hours. Because all of these buildings have these awesome building management systems, they can interface with the grid very easily and take advantage of local utility incentives. I also put a factor of safety on the solar system size of 1.2. From what I can understand, Solar did a similar thing, and it worked out pretty well for them. Should just cover any inconsistencies in modeling. I did assume residential rates for the residual utility charge. With apartment complexes, you might be on time of use, but it is possible in a lot of states to chop up the individual apartments and the solar system to get on residential rates. That just might cost a little bit more. The SRECs and any sort of state incentive, again, I left all of those out, and then along with utility incentives. So there's a lot of money to be had out there from incentives that I did not consider. Another consideration is lower occupancy rate. These projects are relatively unique. They're cool. For the tenant, they can move in and feel good about themselves because they're living in a green project. And people get really excited about that. So these projects do tend to have lower occupancy rates, which will drive up your value. One of the last things is market stability. Again, just with that product differentiation, you're going to see that these projects will probably hold up better in times of market instability. And then they're future-proof. They're, as I mentioned before, more resilient, but also the time of use and demand reduction capabilities are going to allow these buildings to respond a lot better as utilities start to shift more towards time of use infrastructures. In conclusion, net zero building is viable mostly in climate zone 5A in the Northeast, but I'm really excited about these findings because it works today, and that's a really awesome thing. And I think, as we're moving forward, we need to work to not only keep housing affordable, but also keep it clean for our future generations. And, there might be some projects where developers are taking more of a hit financially, but it's going to be more than worth it in the long run when we're, saving ourselves from all the headache of climate change. Thank you very much. I'm open to questions now.
So sorry, questions for Alex?
Ramesh, I have a comment and a question. This is Revis again. Well, first of all, it's an excellent presentation because I think it does go to the question of how transferable are these ideas regionally across the United States. And I think widespread deployment will be the question mark and whether this will make an impact. The question I had was, in all of your assessment of the buildings, both the construction, the costs and everything, any significant or notable differences in how durable and maintainable
these net zero energy buildings would be in relation to a typical residence or apartment building? Is there any appreciable difference that would be anticipated?
Yeah, so there's two elements to that. The first of which is the actual, the building shell. And these buildings as a whole, because they're actually verifying all of their air sealing and they're trying to hit these very specific energy goals, your GCs and all the contractors are going to be watching the quality of the construction a whole lot more. So these buildings are going to be built to higher standards. So, I would expect them to be built better and last longer. Now, on the flip side of that, with the mechanical ventilation and some of the heat pumps and some of this other stuff, you're going to have more mechanical elements, especially along with the solar. You're going to need to replace the inverters every 10 years or so. So there should be some increased operational costs.
Okay, I appreciate that. I just wanted to also just add a comment. This is really more of an idea for continued research as it relates to this project, but I'm not sure, your involvement or others who maybe want to do work off of this, but I think an interesting question. I mean, all the analysis on the incentives and the impacts they have on the finances and all that are really valuable, and that in itself will be a work that will go on for years to come, I'm sure, because of the many areas you noted could also be considered in the analysis and weren't. I think another question, though, would be really valuable is to understand just how high energy costs would have to be for widespread deployment of net zero buildings to occur without incentives. Now that's complex because I'll involve some economic analysis, but I think that would be a very interesting and valuable analysis. And a spinoff of that would be to consider that same question if carbon were costed and those costs started to surface in energy costs. That could be a parametric analysis. So I don't know, Ramesh, maybe that's as much addressed to you as it is to Alex. That could be something interesting to look into as another project related to this work. So that's my comment.
Yeah, I would, I know it was a question, but I would respond to that by saying that because of when I was calculating the net disposition value and the cashback periods across the United States, each of those were calculated against the average utility fee in each state. So there is some price and sensitivity calculated in that. It's not necessarily reflected in this presentation, but it is reflected in the research. And what we'll see is that the cost of energy very greatly impacts how accessible this is. And then as far as incentives go, net metering is a state mandated incentive for solar. In the states that have strictly reimbursed solar at the avoided cost of energy are not financially viable for solar at this moment. And I think we're going to need to either see energy costs rise or battery costs significantly decrease before we'll see that happen. But in a lot of states, the solar payback period is somewhere between 10 to 14 years, and that's with net metering. So it's just it's the state of where we're at today.
Any other questions for Alex?
Alex, this is Al Rotz. I said, I remember talking to you about this project last fall and congratulate you on taking it to the next level. I think the real challenge here, when you talk about most construction contractors, especially residential, their idea is to use construction grade materials, get their money out of you as fast as they can and move on, and not to have a premium construction. So I think the challenge here is going to be to sell this concept to people, to the contractors, convince them that there's going to be a market there and people will pay this rate. if your analysis is correct, it seems like a no-brainer. The question should be, why aren't more people doing this? It's the right thing to do, and as you noted, there's very little incremental cost in the long run. So, like I said, I think the challenge going forward is to sell this concept to a lot more contractors out there.
Yeah, I would agree with that. I think one thing that Burns Realty Group did a great job of is keeping the general construction of the project as similar to traditional construction as possible. You know, for your framing, it's conventional framing just with slightly larger walls. The air sealing requires a little bit more effort and work along with a lot of the insulation. So, you know, it's definitely on the GCs to make sure that they're counting all their subs to make sure that they're using the proper materials as you specified. But the complexity of these projects from a actual construction perspective is not significantly worse. And I think that's very important.
Great.
Rudy, I have one other comment. I certainly agree with Al's comment, but I'd like to clarify that the contractors who are taking somebody else's design are not likely to promote this. It really needs to mostly come from architect engineering firms and project managers who have an influence during the initial proposal. So it comes from architect firms, including the cost benefit analysis. Contractors are not, quite frankly, the right venue, in my opinion, to take this to the market. It needs to come from project managers and architect engineers. The other item that I would suggest, and I agree wholeheartedly with the presentation, I love your innovative approach to selecting these locations, is we need to be aware that net metering for many utilities is a social rate-making enterprise. The utilities are not going to be reimbursed for these charges, and we'll have to do rate filings to supplement those costs. Net metering is a controversial topic in a lot of states for that reason, like Nevada, where they basically don't do it because it supplements other rates. So yes, this is the right thing to do. My point mainly is don't expect to ever see annual net metering instead of monthly. That would probably be stepping over the line for most public utility commissions. They're not going to be willing to go to annual net metering. At best, many of them will continue their monthly net metering so that the supplement, their subsidy in their rate making does not get too high. Great presentation, Alex. Thank you.
Hey, Alex, I have a real quick question. It was a good presentation. I know you said that you were getting paybacks in 3 years. That's a really good message to the end use customer. And I think there's a lot there that really blows the doors off of some of these contractors to go out and sell this product. What would you think would happen if you were to oversize the I don't know if you were positioned with a whole bunch of different rooftops to analyze. I'm seeing like that oversizing rooftop really helps the customer much more see the realization of the payback. Plus, a lot of the rooftop configurations have almost been in collusion sometimes between the utility, the intermediary installer, and even other parties like cities that are effectively getting some of the rates. And I was wondering if that would really accelerate things, because I think maybe it was Revis that said, I'm not sure what would move this into high gear. And I'm thinking after your presentation that oversizing the rooftop solar to accommodate, and I know there's engineering concerns there, maybe, maybe not. I think they're overblown, but oversizing it may just make a whole big of a difference. I think in California, where they're only doing 3 kilowatt hours, is just like underserving. I'm not even sure how they derived that rule for new housing. What are your thoughts on that?
Yeah. First off, the costs for the solar for this project were based on carports. Just because I believe the net surface area needed for the solar relative to the available space on the rooftops was larger. I didn't look into it that deeply. I did change the costing for the rooftops to account for vaulted instead of flat, just because it's significantly cheaper. So, you know, if you had southern oriented rooftops, you would save a lot more money by installing solar on that instead of building a whole carport structure. You would also save carbon. What, to your point about the size limiting of the systems, in a lot of states, they've got more stringent size limiting. The solar on this was oversized at 1.2, but I also just, for the sake of the economics, assumed that there wasn't going to be any excess generation. Just maybe some of the tenants would use the building a little bit more efficiently.
Okay, that's a good answer.
Yeah, what I have seen, just to round it off, is you're not going to be getting a lot of great payback from oversizing solar, because any net excess generation pretty much across the board is going to be sold at the avoided cost of energy, whether that's at a net meter reconciled on a monthly basis or an annual basis. And the avoided cost of energy is just not viable for solar.
Okay, good, thanks.
Any other questions for Alex? Okay. So this is the last of the presentations, and so I thought that we can have a general discussion. Any questions to anybody, myself included, about what you heard? Anything else? Or if you have thoughts or comments on what you heard, want to share that?
Well, Ramesh, this is Revis. I'll offer one general comment, which I'm sure we can discuss further tomorrow. I think the projects showed generally some progression and perspective, which I appreciate. In that, I think all the projects were trying to think a little more broadly about the topic of research. How's it going to translate to a broader scale? I mean, these feasibility of projects, feasibility of things, whether it's marine energy or it's virtual power plants or net zero energy buildings, those are valuable things as first steps, because you do have to understand the mechanics. The devil's always in the details. But I think the difficult questions lie in scalability, whether some of these ideas can have broad scale application, therefore make a big difference, whether it's economic impacts or impacts on greenhouse gas emissions and stuff. So I think the projects are all trending a little bit, especially the last two, towards that direction a little more, and I think that's good. Me personally, I think that's trying to move in the direction of answering that question of scalability is an overarching value for taking a lot of the projects in that direction. So that's my comment.
Any other thoughts, comments? Okay, I know it's been a long, almost 2.5 hours, yes. Actually, we're right on time. Because I think Susan had set aside some time for you guys to fill out the Google forms and send it back. So I really appreciate your patience, and we will be meeting a number of you tomorrow. Lots of you at the IAC meeting. Some of you will be here in person. That's great. And I look forward to talking to all of you tomorrow. Right? Students, any thoughts you want to share with them?
It was really supportive feedback, supportive ideas, and we are looking to enhance our projects.
Can't really hear what he was saying. Sorry.
I said it was really supportive and fruitful discussion with the audience. It was a fruitful discussion with the audience and their feedback about our projects. And we are looking to enhance our projects in order to get a realized outcome from our projects.
Anything else?
Yeah, thank you all for coming. Really appreciate the comments and discussion.
Rudy, this is Jim Robinson. I just want to compliment all the presenters and a special welcome to those from Egypt. I spent a couple of years in Egypt as a contractor and consultant with the Egypt Electric Authority. I'm glad to see you. Hope you enjoyed your time here and a great presentation and project. But thanks to all the presenters. Thank you.
Thank you.
Thank you, sir.
All right. Well, thank you. Thanks for your patience. You stuck around for 2.5 hours, and I really appreciate it. And we'll see you all tomorrow.
Thanks, Ramesh.
All right. See you.
Thanks, everyone.